A photon leaves a distant star and begins crossing the darkness between worlds. Perhaps the star is only a few light years away. Perhaps it belongs to a galaxy so distant that the light must travel for billions of years before reaching Earth. During that journey, entire civilizations could rise and disappear. Stars could be born, burn through their fuel, and collapse. Galaxies could slowly change shape. Planets could form from clouds of dust and eventually become worlds. From our perspective, an almost unimaginable amount of time may pass while that single particle of light continues across the universe. And yet, hidden inside Einstein's theory of relativity is a statement that seems almost impossible. Along the path followed by that photon, the quantity physicists call proper time is exactly zero. Not extremely small, not almost zero. Zero. A beam of light may cross billions of light years, according to clocks scattered throughout the universe. But the space-time path connecting its emission and absorption accumulates no proper time at all. This is sometimes simplified into the statement that light does not age. And although that phrase captures something real, the physics underneath it is far stranger than the idea of a photon simply having a very slow clock. To understand why, we first have to abandon one of the most natural assumptions we make about reality, that there is one universal time flowing equally for everything. It certainly feels that way. You wake up in the morning and hours pass. Your body changes. Your cells perform chemical reactions. Your heart beats. The earth rotates beneath you. Somewhere else, another person watches another clock count through what appears to be exactly the same sequence of seconds. For most of human history, there seemed to be no reason to question this. Isaac Newton built his physics around essentially this picture. Space formed the enormous stage on which the universe existed, while time flowed independently in the background. Objects could move through space at different speeds, but time itself remained universal. 1 second here was fundamentally the same as 1 second anywhere else. Then came Einstein. In 1905, special relativity replaced this intuitive picture with something far stranger. Einstein began with two principles. The laws of physics should work the same way for observers moving uniformly relative to one another, and the speed of light in a vacuum should be the same for every such observer. That second principle creates the problem. Imagine standing beside a railway while a train moves past you. Someone on the train throws a ball forward. The passenger measures the speed of the ball relative to the train, while you measure the speed of the train plus the speed of the ball. Ordinary velocities combine. Light refuses to behave this way. Imagine replacing the train with an extraordinarily fast spacecraft. It passes Earth at half the speed of light, and someone aboard switches on a flashlight pointing forward. You might expect the light to move away from Earth at 1.5 times the ordinary speed of light. It does not. The astronaut measures the beam moving at the speed of light. You measure the same beam moving at the speed of light. Accelerate the spacecraft further, and the result remains unchanged. Something has to give, and what gives is our ordinary understanding of space and time. Different observers can disagree about distances. They can disagree about how much time passes between events. They can even disagree about whether distant events happen simultaneously. What remains consistent is the deeper structure connecting space and time. This is spacetime. Instead of imagining yourself as an object moving through three-dimensional space while a universal clock ticks somewhere in the background, relativity describes your existence as a path through four-dimensional spacetime. Physicists call this path a world line. Every moment of your life belongs somewhere along it. Your birth lies on that world line. So does this moment. So does every future event you will ever experience. And along that path, something accumulates. Proper time. Proper time is the time measured by a clock traveling with you along your world line. It is, in a physical sense, your own elapsed time. If 10 seconds of proper time pass for you, your watch advances 10 seconds. Your heart and brain evolve through those 10 seconds. Atomic processes inside your body proceed through 10 seconds. But another observer following a different path through spacetime does not necessarily accumulate the same amount. This is where relativity stops being merely strange and becomes deeply personal. Imagine two identical clocks beginning side by side. One remains on Earth. The other travels through space at an enormous fraction of the speed of light before eventually returning. When the clocks are brought together again, they can disagree. The traveling clock records less elapsed time. This is not because movement damaged its mechanism. An atomic clock, a mechanical clock, a biological organism, and an unstable particle all obey the same underlying effect. The difference belongs to space-time itself. We call it time dilation. And although the effect is tiny at ordinary speeds, it becomes enormous as an object's speed approaches the speed of light. At 90% of light speed, the difference is already significant. At 99%, it becomes dramatic. Push closer still, and the amount of proper time accumulated by the moving object becomes smaller and smaller compared with the time measured by another observer. But there is an important boundary. A spacecraft can approach the speed of light. A proton can approach it. An electron can approach it. Anything with mass can move closer and closer to that speed, but it can never reach it. Light is different. A photon has no rest mass, and in vacuum it travels at the invariant speed built into spacetime itself. And at that speed, the geometry changes category. The world line of an ordinary massive object is called timelike. Along a timelike path, proper time accumulates. A clock can travel along it. An object can age along it. The path of light is called null. And along a null path, the space-time interval that determines proper time becomes exactly zero. This is why saying that light merely experiences extreme time dilation can be misleading. A photon is not simply an astronaut traveling incredibly fast with an incredibly slow clock. It belongs to a fundamentally different category of motion through spacetime. For you, 1 second can pass. For a fast-moving astronaut, less than 1 second may pass between appropriately compared events. But along the null trajectory followed by light, the proper time between emission and absorption is zero. A photon could leave the sun and reach Earth about 8 minutes later according to our clocks. A photon could cross the Milky Way for tens of thousands of years according to clocks associated with the galaxy. Another could travel across cosmic distances for billions of years before finally entering a telescope. The external travel times can be completely different. The null character of the paths is the same. Zero proper time accumulates along each one. But now we reach a dangerous question. If no proper time passes along the photon's path, does that mean the photon experiences its entire journey instantly? Does a photon emitted billions of years ago somehow see its creation and absorption happening at the same moment? Does the universe appear frozen to light? These questions sound reasonable. They are also where many explanations of relativity go wrong, because relativity allows us to describe the universe from the reference frame of an astronaut, a planet, a particle, or almost anything else moving below the speed of light. But there is one reference frame the theory does not allow us to construct: the reference frame of light itself. There is no valid frame in which a photon is sitting still, and that means the phrase "from the photon's perspective" hides a problem far deeper than it first appears. To understand why light does not age, we will have to explore not only what proper time means, but why the universe refuses to give a photon a clock in the first place. The idea that a photon accumulates zero proper time immediately invites us to imagine something almost irresistible. We picture ourselves somehow becoming light. We imagine accelerating faster and faster until the stars begin to distort around us. Distances contract. Clocks throughout the universe appear strange, and finally, at the speed of light itself, time seems to disappear completely. From there, it feels natural to ask what the universe would look like. Would everything happen at once? Would the entire distance between a distant star and your eye collapse into nothing? Would a photon somehow exist in an eternal instant between its creation and destruction? These images are fascinating, but they quietly cross a boundary that relativity does not allow us to cross. The mathematics lets us approach the speed of light as closely as we like. It does not let us stand on that boundary and look outward. To see why, imagine a spacecraft chasing a beam of light through empty space. At first, the spacecraft is moving slowly. The astronaut measures the beam and finds that it is racing away at approximately 299,792 kilometers per second. Then the spacecraft accelerates until it reaches half the speed of light. Ordinary intuition suggests that the beam should now be escaping at only half its original speed. But when the astronaut measures it again, nothing has changed. Light is still moving away at exactly the same invariant speed. So the astronaut accelerates further. 90% of light speed. The beam still moves away at light speed. 99%. Still the same. 99.999%. Still the same. No matter how closely the spacecraft approaches the beam's speed, the astronaut never begins to catch up in the way they would catch an ordinary moving object. Light never appears to slow down relative to them. This is one of the central consequences of special relativity. The speed of light is not simply another speed that happens to be extremely large. It behaves as a fundamental feature of spacetime. Every inertial observer measures the same value for light in vacuum, and space and time adjust between observers in precisely the way necessary to preserve that value. This is described mathematically by the Lorentz transformations. These transformations allow physicists to translate measurements between observers moving relative to one another. If one observer says a certain distance is 10 meters, another moving observer may measure something different. If one says two distant events occurred simultaneously, another may disagree. If one measures an hour between two events, another may measure a different amount of time. None of them is necessarily wrong. Space and time individually depend on the observer, but the deeper space-time structure remains consistent. And the Lorentz transformations work perfectly well, whether you are moving at 10%, 50%, 90%, or 99.999% of the speed of light. Then you try to reach exactly 100%. Something breaks. The mathematical factor involved in the transformation becomes undefined. There is no valid Lorentz transformation that takes an ordinary observer and transforms them into a reference frame moving alongside light. In simpler terms, there is no reference frame in which a photon is at rest. That statement is much more important than it initially sounds. For an astronaut, we can imagine placing a clock inside the spacecraft. We can ask what that clock measures. We can define distances relative to the spacecraft. We can describe what happens at the astronaut's location at each moment of their journey. We can do the same for Earth. We can do it for a planet orbiting another star. We can even do it, at least locally and conceptually, for tiny massive particles traveling extremely close to the speed of light. But we cannot attach an ordinary rest frame to a photon. There is no coordinate system in special relativity where the photon is sitting motionless while the universe moves around it, and therefore there is no physically meaningful photon clock that sits beside the photon counting seconds. This is why the statement that a photon experiences no time needs to be treated carefully. What relativity actually tells us is more precise. The proper time between events connected by the photon's null trajectory is 0. That is a statement about geometry. It is not a description of experience. Consider a photon leaving a galaxy 1 billion light years away and eventually entering a telescope on Earth. The emission and absorption are clearly two different events. They happen at different locations in spacetime. According to our cosmic description, roughly 1 billion years may separate them, with additional complications from the expansion of the universe. Yet the spacetime interval along the light-like path connecting them is null. Proper time along that path is 0. It is tempting to transform this into a story in which the photon somehow regards the two events as simultaneous. But relativity provides no photon rest frame from which such a statement could be measured. There is simply no valid photons watch, whose display we can consult. The distinction may seem technical, but it protects us from drawing conclusions that the theory itself does not support. 0 proper time does not mean emission and absorption become the same event. They remain separated in spacetime. It does not mean the photon watches the universe fast forward infinitely quickly. It does not mean the photon sees all distances compressed into a single point. Those pictures arise when we take formulas describing observers moving below light speed and push them beyond the point where the concept of an observer's rest frame remains valid. The real result is quieter and stranger. Light traces a kind of path through spacetime that no massive object can trace. Massive objects follow time-like paths. Light follows null paths, and the distinction between them is absolute. Imagine spacetime around you as containing a structure called a light cone. At every event, light can travel outward along the surface of that cone. Massive objects must travel inside it. They can move slowly through space or incredibly quickly, but their future world lines remain within the boundary established by light. Outside the light cone are events that cannot be reached without traveling faster than light. The surface itself is special. It is the boundary of causality. Light lives on that boundary. This gives the speed of light a meaning much deeper than the speed of electromagnetic radiation. It is the maximum speed at which causal influence can propagate through ordinary spacetime. It determines which events can communicate with which other events. If the sun somehow changed at this moment, Earth could not respond immediately. Information about that change cannot reach us faster than light. The influence must travel across the approximately 150 million kilometers, separating Earth and the sun, taking a little more than 8 minutes. Until that information reaches us, the event at the sun lies outside the portion of spacetime that can yet affect us. Light defines that boundary, and because photons are massless, they naturally travel along it. This also explains why a photon cannot simply slow down in empty space. We often imagine speed as something an object can choose, depending on how much energy it has. A car can move at 10 kilometers per hour or 100. A spacecraft can coast slowly or accelerate rapidly. An electron can possess different velocities depending on its energy. A free photon in vacuum does not have that freedom. It travels at the invariant speed. Giving a photon more energy does not make it travel faster. Instead, the additional energy appears as a higher frequency and shorter wavelength. A low-energy radio photon and an extremely energetic gamma-ray photon both travel at the same speed through vacuum. Their energies may differ enormously. Their frequencies may differ enormously. Their wavelengths may differ enormously. Their speed is identical. Massive particles behave differently. Give an electron more energy, and its speed can increase. But as that speed approaches the invariant speed, each additional increase becomes more difficult. More and more energy produces smaller and smaller increases in velocity. No finite amount of energy can accelerate a massive object all the way to the speed of light. This is not because our engines are too weak. It is not because we have not discovered the correct fuel. It is built into relativity. Massive particles remain on time-like world lines. Massless particles, such as photons, occupy null trajectories. The two categories approach one another mathematically, but a massive object cannot simply cross the boundary and become a light-speed observer. And this makes the photon's zero proper time much less mysterious. It is not that light possesses a clock that has somehow been slowed until its hands stop moving. There is no such clock. The null trajectory itself has zero proper time. The geometry does not provide the kind of elapsed internal time that exists along your world line. You are traveling through space-time on a time-like path right now. Your body changes. Your thoughts unfold. Chemical reactions proceed. Atomic clocks beside you would tick. Proper time accumulates continuously along your history. A photon passing through the room belongs to another category entirely. It may have been created inside a lamp only nanoseconds earlier. Another photon entering through a window may have left the surface of the sun more than 8 minutes ago. Another arriving at a telescope may have crossed interstellar space for centuries. From our clocks, these journeys possess very different durations, but all are null trajectories. And along each null trajectory, proper time remains zero. Yet this raises another puzzle. Because photons clearly do things, they carry energy from the sun to Earth. They strike electrons. They are absorbed by atoms. They change direction. Their wavelengths can stretch as the universe expands. Gravity can bend their paths. They can begin as one frequency and eventually be measured at another. So if light does not age, how can light change? If there is no internal clock ticking along a photon's journey, how can a photon travel through a changing universe and emerge with different properties? The answer depends on separating two ideas that feel almost identical in everyday life, but become very different in relativity. Aging and change are not the same thing. And once we understand that distinction, a photon that crosses billions of years without accumulating a single moment of proper time begins to seem less like a paradox and more like one of the most elegant consequences of space-time itself. A photon does not accumulate proper time along its path, but that does not mean nothing can happen to it. This is where one of the most important distinctions in the entire story appears. Aging and change are not the same thing. Aging refers to internal evolution along a world line, the kind of evolution measured by proper time. Change is broader. A photon can change because of its relationship with matter, gravity, motion, and the expanding universe, even though no proper time accumulates along the null path it follows. The easiest example is redshift. If a light source moves away from you, the light you receive is shifted toward longer wavelengths and lower frequencies. This is similar in spirit to the Doppler effect with sound. An approaching ambulance sounds higher in pitch, while a receding one sounds lower. With light, the effect changes the measured wavelength, and therefore the measured photon energy. A photon detected at a lower frequency carries less energy than one detected at a higher frequency. So from one observer's perspective, light can arrive redshifted. From another, it may be measured differently. The photon has not aged in the way a massive object ages. It has not been carrying an internal clock that slowly altered its properties. The measured energy depends on the relationship between the photon and the observer. Gravity can change what we measure as well. When light climbs out of a gravitational field, it is gravitationally redshifted. Its wavelength increases and its measured frequency decreases for an observer higher in the gravitational potential. Light falling deeper into a gravitational field can be blue shifted instead. Again, this does not require an internal aging process inside the photon. The geometry of spacetime changes the relationship between emission and detection. This becomes even more dramatic across the expanding universe. Space itself expands on cosmic scales, and light traveling across those expanding distances can have its wavelength stretched along with the expansion. This is cosmological redshift. A photon emitted billions of years ago might begin at a short wavelength and eventually arrive at Earth at a much longer one. The cosmic microwave background provides one of the most powerful examples. Those photons were released when the universe was only about 380,000 years old. At that time, the universe was much hotter and denser. The radiation had wavelengths corresponding to a temperature of roughly 3000 Kelvin. Since then, the universe has expanded enormously. The wavelengths of those photons have stretched with it. Today, that ancient radiation is observed as microwaves at a temperature of about 2.7 Kelvin. The photons have crossed almost the entire age of the observable universe as measured by cosmic clocks, and their energies today are far lower than when they were released. And still, along each null path, proper time remains zero. This is one of the clearest demonstrations that a photon can change without aging. Its relationship to the universe changes. Its measured energy changes. Its wavelength changes. But this is not the same thing as an internal clock ticking. Photons can also be absorbed. Imagine sunlight reaching a leaf. A photon from the sun encounters a molecule inside the leaf and transfers its energy. The photon ceases to exist as that photon, while its energy becomes part of the molecular processes that eventually contribute to photosynthesis. That photon may have spent around 8 minutes traveling from the sun to Earth, according to our clocks. Along its null trajectory, no proper time accumulated. Then it is absorbed. Its existence simply ends in that interaction. The reverse process happens constantly as well. An atom can transition from a higher energy state to a lower energy state and emit a photon. That photon is created at the moment of the interaction and immediately begins traveling along a null path. Photons therefore have beginnings and endings. Zero proper time does not mean eternal existence. A photon can be created and destroyed. What it does not do is age internally between those events. Scattering provides another example. A photon can collide with matter and change direction. In some interactions, it can also transfer part of its energy to another particle. Compton's scattering famously demonstrated this behavior. When high-energy photons scatter from electrons, the outgoing photons can have lower energy and longer wavelengths, while the electrons recoil with the transferred energy and momentum. The photon changes. Its direction changes. Its energy can change, but its speed in vacuum remains the invariant speed, and there is still no proper time accumulating along its null motion. This distinction becomes especially useful when thinking about stars. The light reaching you from the sun does not necessarily have a simple history beginning directly in the solar core. Energy produced by nuclear fusion deep inside the sun can take an extremely long time to work its way outward. The solar interior is so dense that radiation is repeatedly absorbed, scattered, and re-emitted. The energy gradually migrates toward the surface through an enormous number of interactions. The important thing is that the same individual photon does not spend tens of thousands of years traveling from the solar core to the surface. Photons are repeatedly destroyed and new photons are created. What persists through that journey is the energy, not one immortal photon. Once a photon finally escapes from the sun's surface, its trip to Earth is much simpler. It crosses interplanetary space in a little over 8 minutes by our clocks, and may eventually be absorbed by your skin, a leaf, the ocean, or a solar panel. The journey ends there, and throughout that final flight, proper time along the photon's null path remains zero. This gives us a much cleaner way to think about light. A photon is not frozen. It is not outside the universe. It is not untouched by reality. It can transfer energy and momentum. It can be bent by gravity, scattered by matter, redshifted by expansion, absorbed, or created in a new interaction. What it does not possess is the same kind of personal elapsed time carried by massive objects. Massive objects age from within. Photons change through their relationships and interactions. That difference is built into space-time itself. And once we recognize that, the next question becomes unavoidable. Why does light occupy this special boundary at all? Why must massless particles travel at exactly one invariant speed? And why does that speed divide the universe into paths that accumulate time and paths that do not? To answer that, we have to look more closely at the geometry of space-time itself. Why should the speed of light have anything to do with time? At first, these seem like completely different ideas. Speed describes motion through space. Time describes how long things last. Yet relativity revealed that the two cannot be separated so easily. The reason light accumulates no proper time is ultimately hidden inside the geometry of space-time itself. Think first about ordinary space. If you walk 3 meters forward and 4 meters sideways, the total straight-line distance between your starting point and ending point is 5 meters. Someone could rotate their coordinate system and describe your movement differently, but they would still calculate the same total distance. The coordinates change. The distance does not. Space-time has something similar called the space-time interval, but unlike ordinary distance, space and time enter the equation differently. That difference creates separate categories of paths through space-time. For massive objects, the path is time-like. For light, the path is null. Along a time-like path, the space-time interval allows proper time to accumulate. A clock can follow that path. A person can follow it. A planet, atom, proton, or any other massive object can follow it. A null path is different. Along the path of light, the contribution from motion through space balances the contribution from time in precisely the way that makes the space-time interval zero. And because proper time is derived from that interval, the proper time is also zero. This is not something the photon actively does. Light does not somehow stop its own clock. The geometry of its path simply contains no proper time. One useful way to visualize this is with a light cone. Imagine yourself at one event in space-time, here, right now. Light leaving you spreads outward in every direction. If we simplify space and draw time vertically, those light rays form the surface of a cone extending into the future. Everything you could physically reach while moving slower than light lies inside that cone. The surface itself belongs to light, and anything outside it is too far away to be reached from your current event without exceeding the speed of light. This means the speed of light does more than tell us how quickly photons move. It defines the structure of cause and effect. If something happens on a star 10 light years away, information about that event cannot reach Earth tomorrow. The earliest possible signal requires roughly 10 years to cross that distance. Until then, Earth cannot be influenced by that event. Light therefore marks the boundary of what can causally connect different regions of spacetime, and photons travel exactly along that boundary. Massive objects remain inside it. This also reveals why adding more energy to a photon does not make it move faster. A radio photon carries far less energy than a gamma ray photon. Their frequencies and wavelengths are enormously different, but in vacuum both travel at exactly the same invariant speed. More photon energy means higher frequency, not greater speed. For a massive particle, the situation is different. Give an electron more energy, and you can accelerate it. As its speed becomes closer to the speed of light, however, increasingly large amounts of energy produce increasingly small increases in velocity. You can reach 90%, then 99%, then 99.9%. You can keep adding nines. But a massive particle never reaches the boundary. No finite amount of energy can accelerate an object with mass to exactly the invariant speed. This creates an incredibly sharp distinction in nature. A particle with mass follows a time-like world line and accumulates proper time. A massless particle follows a null trajectory and accumulates none. Even an incredibly small mass changes the situation. Neutrinos provide a beautiful example. For a long time, physicists wondered whether neutrinos might be completely massless. But experiments showing that neutrinos oscillate between different types demonstrated that they possess mass, although extraordinarily little. That tiny amount is enough. Neutrinos can travel extremely close to the speed of light, but not exactly at it. Their world lines remain time-like rather than null. Proper time therefore accumulates for them. The difference between a photon and a neutrino is not simply that one moves slightly faster. They belong to different geometric categories. And this is why the phrase light does not age points towards something much deeper than time dilation. A fast astronaut still ages. A particle moving at 99.999999% of light speed still accumulates proper time. Perhaps incredibly slowly, relative to another observer, but never exactly zero. Light is different because it sits precisely on the null boundary. There is no gradual final step where the astronaut simply accelerates a little more and becomes a photon-like observer. The boundary cannot be crossed by ordinary acceleration, and this tells us something profound about the universe. The speed of light is not special merely because light happens to travel at that speed. Rather, space-time possesses an invariant speed, and massless particles travel at it. Light reveals the structure that was already there. The constant we call the speed of light is woven into the relationship between space, time, and causality. This is why every observer measures it identically. This is why massive objects cannot reach it. And this is why null paths accumulate zero proper time. The strange behavior of photons is really the strange behavior of spacetime. A photon simply follows the geometry available to something without rest mass. And suddenly our original question changes again. We began by wondering how light could travel for billions of years without aging. But those billions of years belong to clocks following time-like paths through the universe. Earth ages, stars age, galaxies evolve. Our clocks accumulate proper time. The photon's null path does not. The universe can therefore contain a photon emitted billions of years ago according to our clocks, whose trajectory nevertheless contains zero proper time from emission to absorption. Not because the photon somehow survives an eternity without changing, not because it experiences the journey instantaneously, but because the geometry of its path is fundamentally different from ours. And nowhere is this contrast more dramatic than in the oldest light we can observe. There are photons reaching us today that began traveling when the universe looked almost nothing like it does now. They crossed a cosmos in which galaxies formed, stars were born, planets appeared, and eventually life emerged. Those photons have been transformed enormously along the way, yet their null paths accumulated no proper time. And in the next chapter, we can follow that ancient light across almost the entire history of the universe. Some of the photons reaching Earth today began their journey before stars like the Sun existed, before planets had formed, and billions of years before anything resembling life appeared. They come from an era when the universe was only about 380,000 years old. We detect them today as the cosmic microwave background, a faint glow arriving from every direction in the sky and carrying information from an unimaginably young universe. To understand where this ancient light came from, imagine traveling backward through cosmic history. Today, the universe is filled with galaxies separated by enormous regions of relatively empty space. But as we move backward in time, everything becomes closer together. Galaxies approach one another. Matter becomes denser. Radiation becomes more energetic. Continue far enough, and eventually we reach a universe that looks nothing like the one around us today. The early cosmos was hot, dense, and filled with charged particles. Electrons had not yet become permanently bound to atomic nuclei. Instead, matter existed largely as an ionized plasma. Photons moved through this environment, but they could not travel very far without interacting with charged particles. The universe was effectively opaque. Then expansion changed everything. As the universe expanded, it cooled. Eventually, conditions became cool enough for electrons and nuclei to combine into neutral atoms in large numbers. Once that happened, photons could travel much more freely through space. The universe became transparent. The radiation released from this era has been traveling ever since. Those are the photons we now detect as the cosmic microwave background. From our perspective, their journey has lasted for almost the entire history of the universe. During that enormous span of cosmic time, gravity pulled matter together. The first stars ignited, galaxies assembled, generations of stars lived and died. Heavy elements were created and scattered into space. Eventually, the sun formed, Earth appeared, life emerged, and after billions of years of evolution, humans constructed instruments capable of detecting those ancient photons. Yet along the null paths followed by that light, proper time remains zero. This is perhaps the most dramatic example of the strange relationship between light and time. According to cosmic clocks, the journey is ancient. According to the geometry of the light-like path itself, no proper time accumulates. But the photons did not travel through an unchanged universe. Quite the opposite. When the cosmic microwave background was released, its radiation corresponded to a temperature of roughly 3000 Kelvin. Today, we observe it at only about 2.7 Kelvin. Its wavelengths have stretched enormously. Its photons are now far less energetic than they were when the universe first became transparent. The reason is cosmic expansion. As the universe expands, the wavelengths of freely propagating light traveling across cosmological distances can stretch with it. A photon that began with a relatively short wavelength can eventually be detected with a much longer wavelength. This is cosmological redshift. And once again, it shows why zero proper time does not mean nothing changes. The photon can cross an evolving universe. The distance between large cosmic structures can increase. Its wavelength relative to cosmological observers can stretch. Its measured energy can decrease. And none of this requires the photon to possess an internal clock. The change belongs to the relationship between the light and the space-time through which it travels. This gives us an unusual way of thinking about the night sky. Whenever you look into space, you are looking into the past. The moon appears, roughly as it was a little over 1 second ago. The sun appears as it was about 8 minutes ago. Nearby stars appear years or decades in the past. The Andromeda galaxy appears as it was roughly 2.5 million years ago. And when astronomers observe extremely distant galaxies, they can see light that began traveling billions of years before Earth existed. Telescopes are therefore not simply machines for looking far away, they are machines for looking backward in cosmic history. Light preserves information about distant events and carries that information across the universe until it interacts with something capable of detecting it. A photon entering a telescope may contain information encoded in its wavelength, polarization, direction, and energy. From that information, astronomers can reconstruct properties of objects that may have changed dramatically since the light began its journey. Some of the stars we observe may no longer exist in the form we see them. Some galaxies have evolved. Some stellar explosions occurred millions or billions of years before the photons finally reached our instruments. The light is old according to us, but calling the photon itself old is more complicated. Age normally means accumulated proper time. A human is older today because more proper time has passed along their world line. A spacecraft can carry a clock and measure its own duration. A photon cannot do this. Its null trajectory contains no proper time. So a photon detected after traveling across the universe does not possess an age in the same sense that you, a planet, or a star possesses an age. This sounds almost like a loophole in reality, but it is simply what the geometry says, and it creates an extraordinary contrast. The universe can change enormously between the emission and absorption of a photon, while the photon's own trajectory accumulates no proper time at all. Entire galaxies can form between those two events. Stars can live and die. Planets can appear. Yet the light connecting those events remains null. This is why it is dangerous to say that the photon waited billions of years before reaching us. Waiting is something an object does while proper time passes. For the photon, there is no corresponding elapsed proper time. From our perspective, the journey took billions of years. That statement is perfectly meaningful, but there is no photon rest frame from which we can say the photon personally waited through those billions of years. The distinction is subtle, and it becomes even stranger when we imagine the future. A photon traveling through almost perfectly empty space might continue for an extraordinarily long time before finally being absorbed. Depending on the future evolution of the universe, some photons may travel through increasingly empty cosmic regions for times vastly longer than the current age of the cosmos. External clocks could measure unimaginable durations. The null path would still accumulate zero proper time. Light does not become tired. It does not wear down because it has traveled too far. It does not require fuel to continue moving through vacuum. Its energy can change through cosmological redshift or interactions, but distance alone does not exhaust it. And perhaps this is the deeper reason ancient light feels so strange. We usually associate age with distance into the past. Something that began billions of years ago should itself be billions of years old. For massive objects, that intuition often works reasonably well. For light, it fails. The photon connects two moments that may be separated by almost the entire history of the universe, while following a path on which no proper time accumulates. It is not timeless because it exists outside spacetime. It is timeless in this specific, relativistic sense because of the kind of path it traces through spacetime. And once we see that distinction clearly, one final question remains. If photons can be created, travel along null paths, interact, change energy, and eventually disappear, what does it really mean to say that a photon exists between its emission and absorption? To answer that, we need to move beyond the image of light as a tiny glowing object flying through empty space and look at what modern quantum physics says a photon actually is. After following light across billions of years of cosmic history, we arrive at a question that sounds almost embarrassingly simple. What exactly has been traveling? We speak naturally about a photon leaving a star, crossing space, and eventually entering a telescope. The language makes us imagine a tiny glowing object flying through the universe, almost like an unimaginably small grain of light. But just as electrons are not miniature planets orbiting atomic nuclei, photons are not tiny classical bullets moving through empty space. Modern physics gives us a stranger picture. A photon is the quantum of the electromagnetic field. The electromagnetic field exists throughout space. Light is associated with disturbances and excitations of that field. And when we describe electromagnetic radiation quantum mechanically, its energy comes in discrete units we call photons. This explains why light seems to possess two apparently contradictory personalities. In some experiments, light behaves like a wave. It spreads, diffracts, and produces interference patterns. Send light through two narrow openings, and the possibilities associated with those paths can interfere, producing alternating bright and dark regions. Yet when light interacts with matter, its energy is transferred in discrete events. A detector does not necessarily receive one continuous smear of infinitely divisible light energy. Individual photons can be absorbed one at a time. This is the famous wave-particle duality of quantum mechanics. But the phrase can be slightly misleading because it makes it sound as though the photon sometimes chooses to become a classical wave and at other moments transforms into a classical particle. It is neither in the ordinary sense. A photon is a quantum object. Wave-like and particle-like behavior are different aspects revealed by different kinds of interactions. And this matters when we ask what happens during the enormous journey between emission and absorption. Imagine an atom inside a distant star. The atom changes from a higher energy quantum state to a lower one, and electromagnetic radiation is emitted. In an appropriate quantum description, a photon may be created. Later, perhaps millions or billions of years later, according to our clocks, that radiation interacts with matter again. Maybe it reaches a telescope. Maybe it strikes a grain of interstellar dust. Maybe an atom absorbs it. At that interaction, the photon can cease to exist as a photon, and its energy and momentum are transferred elsewhere. So a photon does not need to be imagined as a permanent object, with an internal history stretching through every moment between those events. It is a quantum excitation connecting interactions through spacetime, and the path associated with its propagation is null. That is why the idea of asking what the photon was personally experiencing during its journey becomes so difficult. There is no internal photon clock recording the trip. There is no rest frame in which we can place the photon at the center and watch the universe move around it. The photon is not an observer. It is part of the physical structure being observed. This becomes even more important when we remember that photons can have very different energies. A radio photon may carry extremely little energy. A visible light photon carries more. An X-ray photon carries much more. A gamma-ray photon can carry vastly more still. The relationship is described by one of the simplest equations in quantum physics. A photon's energy is proportional to its frequency. Higher frequency means greater energy. Lower frequency means less energy. Yet all of these photons move through vacuum at the same invariant speed. The universe does not make high-energy photons faster. It makes them higher in frequency. This is radically different from the behavior of ordinary massive objects. If you give a spacecraft more kinetic energy, you can make it move faster. For light, changing energy changes frequency and wavelength instead. A photon can therefore lose measured energy through redshift without gradually slowing down. A photon from the early universe can have its wavelength stretched enormously by cosmic expansion and still travel at the invariant speed. Again, our everyday intuition fails because it was built around massive objects, and photons are massless. Their existence is inseparable from the null structure of spacetime. There is another subtle point hidden here. When we talk about the same photon traveling across the universe, that language can be useful. But quantum physics does not always support the perfectly classical identity we instinctively attach to objects. Photons are fundamentally identical particles. One photon of a particular quantum state does not contain a microscopic serial number distinguishing it from another identical photon. In more complicated quantum processes, asking which exact photon later corresponds to which earlier photon may not even have a meaningful answer. Nature is not obligated to preserve the individual identity of particles in the way we preserve the identity of cars or people. What remains reliable are the physical laws, quantum states, interactions, and conserved quantities. Energy is transferred. Momentum is transferred. Angular momentum can be transferred. Information about the source can be encoded in the radiation. And eventually another interaction occurs. This is part of what makes light such an extraordinary messenger. Almost everything we know about the distant universe has reached us through some form of electromagnetic radiation. We know what stars contain because atoms leave characteristic patterns in their spectra. We measure the motion of galaxies through shifts in their light. We study planets around distant stars by observing tiny changes in starlight. We reconstruct the early universe using ancient radiation. The photon carries information across distances that no human being could ever physically cross within a lifetime. And yet the messenger itself does not age along the way. A photon emitted before Earth existed can arrive today carrying information about a world that has already changed beyond recognition. The source aged. The universe aged. We aged. The null path did not accumulate proper time. This gives the photon an almost paradoxical role in reality. Light allows us to observe time precisely because light itself follows a path with zero proper time. When you look at the night sky, you do not see the universe as it exists at one universal present moment. You see layers of cosmic history. Different distances correspond to different emission times. The sky is an archive assembled from photons. A nearby star shows you a relatively recent past. A distant galaxy reveals a much older one. The cosmic microwave background carries information from the childhood of the universe itself. Light makes the past visible, but we should resist turning this into the claim that light somehow lives outside time. Photons exist within spacetime. Their emission and absorption are spacetime events. Their trajectories respond to spacetime geometry. Gravity can bend those trajectories. Cosmic expansion can alter the wavelengths we measure. Matter can scatter or absorb them. Light is deeply embedded in the universe. What makes it unusual is simply the kind of spacetime path it follows. Null instead of timelike. Zero proper time instead of positive proper time. And perhaps that is stranger than saying light is timeless. Because timelessness sounds mystical, as though photons escape the rules governing everything else. The reality is almost the opposite. Photons accumulate zero proper time precisely because they obey the geometry of spacetime perfectly. There is no exception, no hidden mechanism, no frozen internal clock. The mathematics of relativity simply assigns zero proper time to a null path. And quantum physics tells us that the thing following that path is not a tiny classical object, but a quantum excitation of the electromagnetic field. Together, those two ideas bring us close to the real answer. Light can cross the history of the universe without aging, because aging belongs to time-like paths. A photon does not follow one. But before we finish, there is one deeper implication worth exploring. Because if time itself is measured differently along different paths through spacetime, then perhaps the question is no longer simply why light does not age. Perhaps the deeper question is why we do. Perhaps the strangest part of this entire story is not that light fails to age. Perhaps it is that we do. Every second you experience becomes part of your history. Your body changes. Your thoughts move from one moment to the next. Chemical reactions occur inside your cells. Memories form. Clocks advance. Whether you are standing still on Earth or traveling through space, proper time accumulates along your path through spacetime. A photon follows a different kind of path. That difference has nothing to do with biology. Aging, in the relativistic sense we have been discussing, begins much deeper than wrinkles, metabolism, or the gradual breakdown of living cells. Before biological aging can exist, physical processes must be able to unfold through proper time. Atoms inside your body change states. Molecules collide and react. Electrical signals move through neurons. Your heart completes one beat and then another. All of these events occur along time-like paths. There is a meaningful interval between one state and the next. You carry a clock through space-time, even if you never look at one. The photon does not. Its trajectory is null, and the proper time between emission and absorption is zero. This creates a beautiful contrast between matter and light. Matter can rest. You can sit in a chair and say that, relative to the room, your position is barely changing. Yet time continues passing for you. Your world line extends forward through spacetime, and proper time continues accumulating. Light cannot do this. There is no state in which a photon simply stops in empty space and waits. A free photon in vacuum travels at the invariant speed. There is no photon rest frame in which it remains at one position while seconds pass around it. For massive matter, rest is possible and aging is unavoidable. For light, rest is impossible and proper time along its path is zero. These are not two unrelated facts. They emerge from the same geometry. And this helps us see why asking what light feels is so difficult. Experience requires change. A thought must become another thought. A clock must move from one reading to the next. A physical memory must contain a state that differs from an earlier state. All of those ideas require an internal sequence, but there is no proper time sequence along a null world line in the same sense there is along yours. This does not prove some philosophical statement about consciousness or experience. Physics does not tell us what it would somehow feel like to be a photon, because the concept of a photon observer is not defined in relativity. There is no valid rest frame from which to ask. The safest statement remains the simplest. Light follows a null path. We follow time-like paths, and proper time behaves differently along them. This distinction also reveals something profound about the idea of a universal present. Right now, it feels as though the entire universe must share this moment with you. Somewhere, distant stars are doing something now. Galaxies billions of light years away must have some current state, even though their light has not reached us yet. Relativity complicates this intuition. Observers moving differently can disagree about whether distant events are simultaneous. There is no single, universal cosmic clock that every observer must agree upon in all circumstances. Your present is not a slice of time that the entire universe is required to share in the simple Newtonian sense. Instead, space-time contains events and relationships between them. Some events can causally influence others. Some cannot yet. Light defines the boundary. This is one reason photons are so central to our understanding of reality. They do not merely illuminate objects. They determine what information can reach us. Everything you see is already in the past. When you look at an object across a room, the delay is so tiny that you never notice it. When you look at the moon, you see it a little more than 1 second in the past. The sun appears roughly 8 minutes in the past. Look farther away and the delay becomes enormous. The night sky is not an image of one universal present. It is a collection of different pasts, and light connects those past events to your present observation. A photon can begin at one event and end at another, while the observers and objects around those events accumulate years, millions of years, or billions of years of proper time. The universe changes around the light. The light connects the change, and this gives us a different way of thinking about our own passage through time. We sometimes imagine time as a river flowing around us, carrying everything equally toward the future. Relativity replaces that picture with something more personal. Different paths through space-time contain different amounts of proper time. Two people can leave one another, travel along different world lines, reunite, and discover that they have aged by different amounts. Neither person's clock was malfunctioning. Neither experienced time incorrectly. Their paths through space-time were different. This has been experimentally confirmed with atomic clocks and with unstable particles moving at high speeds. Time dilation is not an illusion produced by perception. It changes how much proper time physical systems actually accumulate between events. And in that sense, aging is partly geometric. Your age is connected to the length of your world line through spacetime. A photon occupies the limiting case where that proper time length becomes zero. This does not make light immortal. Immortality would imply continuing to exist while time passes. A photon can be absorbed a fraction of a second after being created, according to our clocks. Another can cross intergalactic space for billions of years before interacting. Both can cease to exist. Neither needs to age first. That distinction is important. Light does not defeat time. It does not survive time. Its trajectory simply does not contain proper time in the way ours does. And perhaps that is the quietest way to understand the apparent paradox. When we say a photon can cross billions of years without aging, we are comparing two different measures. The billions of years belong to clocks associated with massive observers and cosmic history. The zero belongs to the proper time along the null trajectory. Both statements can be true. The photon can connect an ancient galaxy to a detector on Earth across an enormous span of cosmic history, while the space-time interval along its own path remains null. There is no contradiction, only geometry that does not resemble our intuition. And this brings us almost to the end of the journey. We began with a photon crossing the universe without aging, and discovered that the answer was not hidden inside the photon at all. There is no mechanism inside light that stops time. There is no special clock frozen at zero. The answer belongs to space-time itself. Massive objects like us follow one kind of path. Light follows another. And in the final chapter, we can bring those two paths together and ask what this strange difference tells us about time itself. We began with a question that seemed almost impossible. How can a photon cross billions of light years without aging? How can something travel from the early universe to a detector on Earth while accumulating no proper time along the way? At first, the answer seems as though it must involve something unusual inside the photon itself. Perhaps light has some special mechanism that freezes time. Perhaps its incredible speed somehow slows an internal clock until it stops. But after following the physics more carefully, we find that the deepest explanation is not really about photons at all. It is about the structure of time. Before relativity, time seemed universal. There was space containing all the objects in the universe, and there was time, flowing independently in the background. Every clock was supposed to be measuring the same underlying cosmic progression. Different clocks might disagree because one was inaccurate, but somewhere beneath those imperfections, there seemed to be one true time shared by everything. Einstein changed that picture. There is no single universal clock ticking identically for every possible observer. The amount of time that accumulates between events depends on the path taken through space-time. Your clock measures your proper time. Another observer following a different world line measures theirs. If you separate, travel differently, and later meet again, those clocks may no longer agree, and neither one needs to be wrong. This is not simply a trick of perception. The difference is physical. Atomic clocks record it. Unstable particles reveal it through their decay times. Modern technologies such as satellite navigation must account for relativistic timing effects to remain accurate. Time is part of the geometry of the universe, and light occupies the most extreme boundary of that geometry. Massive objects follow time-like world lines. Along those paths, proper time accumulates. Processes unfold. Clocks tick. Objects can possess a rest frame. Light follows null paths. Along those paths, proper time is zero. This gives us a cleaner way to understand what we have been calling the timelessness of light. Light has not escaped time. A photon does not leave the universe and enter some separate timeless realm. Its emission occurs at a location and time. Its absorption occurs at another location and time. Between those events, it propagates through spacetime and can be affected by the geometry of that spacetime. The path itself is simply null. That distinction matters because it prevents us from turning relativity into something more mystical than it actually says. A photon emitted from a distant galaxy does not necessarily experience the journey as instantaneous because relativity does not define a valid photon rest frame from which such an experience could be described. The theory gives us something more precise. The proper time along the trajectory is zero, and perhaps the most remarkable thing is that this remains true regardless of how enormous the journey appears to us. A photon crossing your room follows a null path. A photon traveling from the sun to Earth follows a null path. A photon crossing the Milky Way follows a null path. An ancient radiation traveling across almost the entire observable history of the universe follows null paths as well. The distances are different. The travel times measured by external clocks are different. The geometry of the light-like trajectories remains the same. This means that when we describe a photon as being billions of years old, we are using the word age differently from how we use it for ourselves. Your age is measured by proper time accumulated along your world line. A star has a physical history involving billions of years of processes occurring in matter. A planet evolves through time. A photon can be emitted billions of years before we detect it, but there is no corresponding billions of years of proper time along its null trajectory. The universe around the photon ages. The photon does not age in that relativistic sense, and yet it can still carry history. This may be the most beautiful part of the story. A photon can contain information about a moment that disappeared billions of years ago. Light entering a telescope tonight might have left a galaxy before the sun existed. That galaxy may now look completely different. Some of its stars may have died. New stars may have formed. Its structure may have changed. But the radiation reaching us preserves information about what happened at the moment it was emitted. In this sense, light turns the universe into an archive. Every direction we look contains a different layer of the past. We never see the sun exactly as it is now. We see it as it was roughly 8 minutes ago. We never see another star at this exact moment. We see the state from which its light departed. Look deeper into space, and you look deeper into cosmic history. Astronomy is possible because light connects separated events across space-time. And the strange thing connecting those events does not accumulate proper time between them. The messenger does not age with the message. But perhaps there is an even deeper lesson here. Our intuition tells us that time is something everything must move through in exactly the same way. We imagine a universal current carrying stars, planets, people, and photons together from past to future. Relativity shows us something different. There is no single amount of elapsed time that belongs universally to every path between events. Time is woven together with space. Motion matters. Gravity matters. The path matters. For massive objects like us, proper time is unavoidable. We exist along time-like world lines. Our thoughts require sequences of physical states. Our bodies change. Our clocks tick. We remember the past because physical information is stored in structures that evolve through time. Our experience is inseparable from this progression. Light reveals the boundary of that experience. It shows us a path through the same universe where the proper time interval vanishes. And perhaps this is why photons feel so mysterious. They are not merely fast versions of us. A photon is not an astronaut moving so quickly that its watch has almost stopped. There is no final acceleration that transforms our perspective into the perspective of light. We remain time-like. Light remains null. The boundary between those categories is built into space-time itself, and that boundary is also the boundary of causality. No ordinary information can outrun it. No massive object can accelerate through it. Every event you can influence must lie within the future structure defined by light. Every event that can influence you must lie within the corresponding past structure. Light, therefore, does more than allow us to see the universe. It helps define which parts of the universe can be connected at all. And so the original question has led us somewhere unexpected. We asked why photons do not age, but the answer forced us to reconsider what aging means. It forced us to abandon universal time. It showed us that elapsed time belongs to paths through spacetime, and it revealed that light follows the unique boundary where that elapsed proper time becomes zero. A photon may cross billions of years, according to us. It may be redshifted as the universe expands. It may pass through gravitational fields. It may carry information from an ancient star until one final interaction ends its journey. But nowhere along that null path is there a photon clock quietly counting the centuries. There is only emission, propagation through spacetime, and eventually, perhaps, absorption. Between those events lies a path with zero proper time, and that may be the strangest answer of all. Light does not need to escape time. It simply shows us that time was never as universal as we imagined. So perhaps the strangest thing about light is not how fast it moves. It is what that speed reveals about time itself. A photon can leave a distant star and cross an unimaginable distance before finally reaching another part of the universe. From our perspective, years can pass, millions of years can pass, billions of years can pass. Stars can be born and die while the light continues its journey. Galaxies can evolve, planets can form. Entire chapters of cosmic history can unfold between the moment the photon is emitted and the moment it is finally absorbed. And yet, along that path, proper time remains zero. Not because the photon has discovered some way to stop time, not because it carries a frozen clock, and not because it experiences the entire universe in a single instant. There is no valid reference frame in which a photon sits still and watches reality pass around it. Instead, the answer is written into space-time itself. We follow time-like paths. Light follows null paths. Along our paths, clocks tick, bodies change, thoughts unfold, memories accumulate. We move from one moment into the next, carrying our own proper time with us. Along the path of light, that same kind of elapsed time simply does not accumulate. And still, light can change. It can be stretched toward longer wavelengths as the universe expands. It can lose measured energy through redshift. It can curve through gravitational fields, scatter from matter, and eventually disappear when it is absorbed. Zero proper time does not mean nothing happens. It means that aging and change are not the same thing. Perhaps that is why light has always felt so mysterious. It allows us to see the universe, yet it does not move through time in the same way we do. Every photon entering your eyes is carrying information from somewhere else and from some earlier event. The light from the moon brings you a world from slightly more than a second ago. Sunlight brings you an image roughly 8 minutes old. The stars show themselves as they were years, centuries, or thousands of years in the past. And the most ancient light we can observe has crossed almost the entire history of the universe to reach us. The night sky is therefore not really a picture of the universe at one moment. It is a collection of different moments, a layered archive of the past carried to us by light. And perhaps there is something quietly beautiful about that. The universe does not show us its history through a perfect cosmic clock. It sends its history across space-time in photons. Some travel only across a room, others cross galaxies. Some begin their journeys before planets exist and end inside instruments built by creatures who evolved billions of years later. The distances can be enormous. The external durations can be almost beyond comprehension. And still, the geometry remains the same. A null path, zero proper time. So the next time you look toward a star, perhaps remember that the light reaching you is doing something far stranger than simply moving very quickly. It is connecting two events across space-time along a path that contains no elapsed proper time of its own. The star may have aged. The universe may have aged. You may have aged while waiting for that light to arrive. But the light itself followed a different kind of path, and hidden inside that difference is one of Einstein's deepest lessons. Time is not a universal river, carrying everything forward at the same rate. It belongs to the paths we take through space-time. If you enjoyed this journey, subscribe to Science Sleep Theory for more calm explorations into the physics hidden beneath ordinary reality. And if you're listening as you drift toward sleep, you don't need to solve anything more tonight. Somewhere above you, ancient light is still crossing the darkness, carrying information from moments long gone, following the geometry of space-time, and quietly reminding us that time was always stranger than it seemed. Thank you for spending this time with Science Sleep Theory. Sleep well, and keep wondering.